In this particular example, we have a function x squared plus 7x minus 4, and we have a smaller function here, 2x plus 7. So the first thing we do is we let f of x equal to the function with the higher power, so that's equal to x squared plus 7x minus 4. Then we let g of x equal to the other function. The next step is to evaluate the first derivative of the larger function f of x. So f prime x is equal to the derivative of x squared is 2x, and the derivative of plus 7x is plus 7. If we follow the procedure, we work out the multiplier is the coefficient of x in g at x. So the coefficient of x in g at x here is this 2, and we divide that by the coefficient of x in f at x, f prime at x, and the first derivative of x, and we get a multiple of 1. And that's fairly obvious just by inspection. But then we have to test, if we follow the procedure, test if a times f at x, f prime at x, is equal to g at x. So basically, is the first derivative of the bigger function a multiple of the second function g at x? So 1 times f prime of x, so f prime of x is 2x plus 7, is that equal to 2x plus 7? So this term here is f prime of x, this term here of g is g at x, and of course that's true. And once that's true, that means we can then use our general formula, where our general formula is the integral of a times f prime at x times f at x to the power of n is equal to a times f at x to the power of n plus 1, so this is our general formula, over n plus 1, plus we have a constant of integration, although here we have a definite integral. So if I follow this rule here, the integral a is 1, f prime at x is 2x plus 7, f at x is x squared plus 7x minus 4, and we're saying that that is equal to a times f at x plus 7x minus 4. Now at the moment the power here is 1, so n plus 1 up here will give me 2, and then divided by 2. So the power here, you're not bringing this quadratic equation here, x squared plus 7x minus 4, is to the power 1, so when you bring it up it comes to the power 2, and you divide by that power. But we're doing a definite integral here going from 2 to 1. So what we have in this particular case, I should have put the limits here to begin with. We're going here from 2 to 1. So we don't have a definite integral here. An indefinite integral. What we have here is a definite integral here going from 2 to 1. So if I evaluate that, and I bring it out here, that is equal to x squared plus 7x minus 4. So that gives me 2 squared plus 7 times 2 minus 4, all to be squared over 2. So what I basically have done here is I put in the upper limit here. So here and here, if I do it in a different color, I put in the upper limit here, and I put in the upper limit there. And that is equal to minus, And I evaluate the same thing again here, but this time it's the lower limit. I'll use a different color there. I'll use green for that. So it's 1 squared plus 7 times 1. So I'm just using different color code so you can see it clearly. And that gives me 4 plus 14 minus 4 all to be squared over 2 minus, and here we have 1 plus 7 minus 4 all to be squared over 2, and this gives me 14 squared over 2 minus, and here we have, is it what, minus 11, minus 10 to be squared over 2. Now 14 squared, if I remember, is 256 over 2 minus, and minus 10 to be squared is plus 100. So it's 100 over 2. So that gives me 156 over 2, which is 78. So I think that calculation is correct. So that's your definite integral of this function here by going through the procedure. Step-by-step procedure. So here we have question 2 in the handout. So once again, we come along here, we have two functions, and we go to the function with the higher power. So we set here the function with the higher power, f of x, is equal to x to the power of 4 plus 4x minus 5. We let g at x equal to the second function, so g at x is equal to 4x cubed plus 4. The next thing we do is we differentiate f at x, so f prime x, x to the power of 4 becomes 4x cubed plus 4x, so the derivative of 4x is 4. So then we come to the next stage, which is to calculate your multiplier a, and a is you get a by getting the coefficient of x in x cubed in this case, in g at x, which is 4. So you take that 4 there, and you divide it by the coefficient of x cubed in f at x. And this gives us a simple multiplier of 1 again. The question then, can we use our rule? So we say, is a times f prime of x equal to g at x? What that's asking is the first derivative of the larger function equal to, or is it a multiple of the second function? So we put in our equation here, a is 1, f at x is 4x cubed, is that plus 4, so that's my f at x. F prime of x is here, and I'm asking, is that equal to g at x, where g at x is the same function here. G at x is that function there. And the question is, yes it is. Yes, the answer is yes. Therefore, we can use our general formula, where our general formula is given as a times f prime at x times f at x to the power of n is equal to a times f at x to the power of n plus 1 divided by n plus 1 plus your constant of integration. Now we have a definite integral here, so obviously we will be going between the upper and lower limit. Up here, the upper limit is 1, the lower limit is 0. So let's go ahead and differentiate this. So the integral from 1 to 0 of 1, where 1 is equal to a, 1 is equal to a, f prime of x is 4x cubed plus 4 f at x, sorry, g at x, sorry, that's, well, it's f prime of x. G at x is x to the 4 plus 4x minus 5 dx. And following our rule, that is equal to x a times, so 1 times x to the 4 plus 4x minus 5. The power up here is 1, so we raise that power to 2, and we divide by the 2. And we are going from our upper limit here of 1 down to our lower limit here of 0. So if I evaluate those, that's equal to, I'll just fill that much in for the moment, all over 2 minus, I'm going to fill these in first of all, and then I'll leave them like that, and then I'll fill in the upper and lower limit in the color coding. So my upper limit here is 1 to the power of 4 plus 4 times 1 minus 5. My lower limit is I'm putting in 0 to the power of 4 plus 4 times 0 minus 5 over 2. And that's over here squared as well. So if I work this out, that gives me 1 plus 4 minus 5 squared over 2 minus, and on this one we have minus 5 squared, because you have 0 plus 4 times 0, and you have the constant, and here is minus 5 over 2. Now if you look at this term here, you have 1 plus 4 is 5, minus 5 is 0, so all of that goes to 0. And what we're left here with minus 5 here to be squared is plus 25, but we have the minus outside, divided by 2, so that gives me a total of minus 12.5. So that is the definite integral for this function here. Okay, I'll move on to the next one shortly. In this case, question 3, we have a trigonometric function, and you have to know this from your log tables, that you'd have to check your log tables for this to see which one might be the derivative of the other one. And if you check your log tables, you'll see that, or your mathematical tables, you'll see that the derivative of tan at x is equal to, if f at x is tan of x, the first derivative is equal to sec squared x. Okay, so you'll see that in the log tables. So from that we say, well, f at x is equal to tan of 4x. Okay, that means g at x is the other function, which is equal to sec squared 4x. Now, if we differentiate f at x, tan of 4x, following the rules that we have here, we have a chain here. We have the outer function is the tan function, and the inner function is the 4x. So the derivative of that is, the derivative of tan of x is sec squared x. So we would say it is sec squared 4x multiplied by, then for the inner function, it's the derivative of 4x, which is 4, so I put the 4 in the front here. So you're basically using your chain rule there, and you say that the first derivative of f at x, I need the prime symbol there for that, is sec squared 4x multiplied by the coefficient of x when you differentiate the inner function. So you get 4 sec squared 4x. So your next task then is to work out the multiplier. So a is the coefficient of the derivative here, sec squared 4x. The coefficient here is 1 in g at x. So that's the coefficient of sec squared x in g at x. And then you're dividing that by the coefficient of x. sec squared x in f prime of x. So we get a is equal to a quarter. And then the question is a times the first derivative equal to g at x, the other function? And so if we test that out, is 1/4 times the first derivative is 4 times sec squared 4x equal to g at x is sec squared 4x, and you can see that that condition is true. Yes, it is, because quarter times 4 gives you 1. So the condition is true, so that means we can go ahead and use our rule. And our rule is as follows: a times f prime of x times fx to the power of n is equal to a times f of x, and you raise the power by 1 and you divide by the raised power. And that's the general rule that we're going to apply here. So our rule is as follows: from the limit from pi over 16 to 0, so our upper limit is pi over 16, the lower limit is 0, and that our a in this case is a quarter, and then our f at x is tan of 4x, and we're saying originally that was brought to a power of 1, so sorry, I have it here actually as power of 1 times sec squared x. If I just go back on that a little bit, what I'm supposed to put in here actually is the prime of x, the first derivative of x, which is 4 times sec squared 4x. Sorry, I was supposed to put in first derivative of x here, and this is a times first derivative of x, and then we have fx, which is the tan of 4x, like so, and we have our dx here, and that is equal to tan of 4x. A is a quarter, first of all, so I put the a in here as a quarter. I have tan of 4x, but I square that. It's originally to the power of 1, but we add 1 to that with the n plus 1, and I divide by the raised power, which gives me 2 up there, and we're going from here from pi over 16 to 0. So if we then come here and do it bit by bit from lower power to upper power, that gives me the tan of 4 times, and I can put in the upper limit there, that's pi over 16, divided by, and I have 4 times 2 here, 8, minus the tan of 4 times, and I put in the lower limit here as 0, divided by 8, and then this gives me the tan of pi over 4 divided by 8 minus the tan of 0 divided by 8. Now if you remember, the tan of 0 is the sine of 0 over the cos of 0. Tan is sine over cos, and the sine of 0 is 0, and the cos of 0 is 1, so that gives us 0 for the tan of 0. The tan of pi over 4 is 45 degrees, and the tan is the same as the slope of a line, and the slope of a line of 45 degrees is 1. That means that if I have a line that's at 45 degrees, if I go 1 in the x direction, that means I go 1 in the y direction. So the tan of pi over 4 is 1, So that gives me 1 over 8 minus 0. So it's 0.125. And that is the definite integral of this function, which you see up here. Okay, I'll go on to example 4. Example 4 is a simple enough example again. If we look at it here, okay, I might zoom up a little bit there. And we go through the procedure again, and we say f of x is the larger function, x squared minus 6x plus 2, the function with the higher power. G at x is the other function, so it's 6x minus 18. I get the first derivative of f at x, so x squared, the derivative is 2x, minus 6x, the derivative is minus 6. Derivative of constant is 0. Now I get the multiple, and I get that by dividing the coefficient of x here by the coefficient of x here. So it's the coefficient of x in g at x divided by the coefficient of x in f prime of x in the first derivative. And that gives me a multiplier of 3. So the question is a times the first derivative of f at x equal to the other function in the product, g at x? So here we have 3 times, so the question is 3 times 2x minus 6 equal to 6x minus 18? And the answer is yes. So if we look at it here, that's that's the first derivative of f at x, and that's the second function in the product, g at x. So if that condition is true, that means we can use our formula, and our formula says a times f prime of x times f at x to the power of n is times dx is equal to a times f at x to the power of n plus 1 or divided by the raised power of n plus 1. So if I come down here and implement that rule, do we have a definite integral here from 2 to 1? So we have a definite integral, so we're going from 2 to 1. What we have is a times f prime of x, so it's 2x minus 6. Then our function for f at x is x squared minus 6x plus 2 dx, and that is equal to a, which is 3, times x squared minus 6x plus 2. This is here already to the power of 1. Sorry, it's hard to see that. That's to the power of 1. So we raise that to the power of 2, and we divide by the raised power. And here we're going from 2 to 1. Now we can take that constant out to try and make our life simpler. So that's equal to 3 over 2. I can open up a bracket, and then I can put the inner function in here. So it's x squared minus 6x plus 2 minus x squared minus 6 plus 2. So I'm just putting in the sort of skeleton here. That's squared like so. I'll put in the upper limit, which we said was 2. So it's 2 squared minus 6 times 2 plus 2. That's our constant. Now I've taken the 3 and the 2 outside here and opened up the brackets. I probably should have done that in the previous questions to simplify it. But now I put in the upper limit 2 here, and now I'll put in the lower limit, which is 1 squared minus 6 times 1. So if I come along to evaluate these, here, that gives me 3 over 2 times 4 minus 12 plus 2 all to be squared times 1 minus 6 plus 2 to be squared. And if we go to the next line, that's 3 over 2. So 4 plus 2 is 6 minus 12 gives me minus 6 squared. minus, and this one is minus 3, isn't it? 1 minus 3 is minus 5, plus 2 is minus 3 to be squared. So if I work that out, that's 3 over 2 times minus 6 squared is plus 36, minus 9 squared is plus 9. So that gives me 3 over 2 multiplied by, so 25, 27, is it? I think it's 27. So 3 over 2 times that, that's 81, isn't it? Over 2, which is 40.5 when we evaluate it. So that's the definite integral for that function. So we proceed on to the next function after this. Okay, and we'll start in this short. So this is a similar one where the larger function is still brought to the power of 1. It's not brought to a power. So once again, our larger function here, f of x, is equal to 4x cubed minus 9x squared minus 6x plus 16. The smaller function, g at x, is equal to 4x squared minus 6x minus 2. Get your first derivative of the larger function. So 4 times x cubed is 12x squared. 4 times 3 is 12 times x, and the power of 3 goes down to 2. This one here is 2 times 9 is 18x. And this one here is minus 6. Get our multiplier a by dividing the coefficient of g at x by the coefficient of f at x. So that gives me 4 divided by 12, which is 1/3. So next question is a times first derivative of f at x equal to the other function in the product, g at x. So is 1/3 times f at x is 12x squared minus 18x minus 6, and that is equal to, is that equal to 4x squared minus 6x minus 2? Well, let's multiply it out and see. So is 12 divided by 3 is 4, 18 divided by 3 is 6, minus 6 divided by 3 is minus 2. And that is equal to g at x, as you can see here. So the answer is yes. That means we can use our formula. So a times f prime at x, the first derivative of f at x, multiplied by f at x to the power of n dx, is equal to a times f at x. You raise that power from n to n plus 1, and you divide by the raised power. So that's our general formula again. So let's apply it. And this is a definite integral going from 2 to 1. So 2 to 1, that's our upper limit. That's our lower limit. And a, we said, was 1/3. And that is f of x. F prime of x is 12x squared minus 18x minus 6. And then our larger function f of x is equal to 4x cubed minus 9x squared minus 6x plus 16. That's times d at x. So if I write these above it, that's my a, that's f prime at x, and this is f at x. So this is equal to, do I have room down below? Yeah, plenty of room, so write it below. That is equal to 1/3 times, and f at x is 4x cubed minus 9x squared minus 6x plus 16. The power up here is 1, so that becomes 2. and let's just straighten this line up a bit, and you're dividing by 2. And that's running from the upper limit. That's calculated between the upper and lower limits, going from 2 to 1. I can bring the third and the 2 here, so I have a 3 and a 2 here. So I can bring the 6th outside the bracket. And then I can evaluate this function. So it's 4 minus 9 minus 6 plus 16 squared minus 4 minus 9. So I'm leaving room for the limits, plus 16 squared. So that's going to be a very large number. Quite a complex calculation here coming up. So if I put the upper limit in, that's 2 cubed minus 9x squared. So here it's x cubed. Here we have x squared minus 6 times, that should be a 2 here, not a 3. That's a 2 there. And then we'll put the lower limit in on the other side. So 4 times x squared is 4 times 2 cubed, minus 9 times 2 squared, minus 6 times 2 plus 16. On this side, we have 4 times 1 cubed, minus 9 times 1 squared, minus 6 times 1 plus 16. So let's evaluate these. Maybe they work out a bit simpler than we expect. So it's equal to 1/6. Okay, 2 cubed is equal to 8. So 4/8 are 32. 2 squared is 4, so 9 fours are 36. Minus 12 plus 16. And all of that has to be worked out and then squared. And on this side we have 4 minus 9 minus 6 plus 16. So I have them here, and that all has to be squared. So if we work it out, it's 1/6 times, I add this lot up, that's minus 4 to that point. Minus 4 gives me minus 16. So the whole thing here looks like it's all going to be plus 48 minus 48. So it's 0 squared minus, and on this side we have 16 plus 4 is plus 20, and we have 9 and 6, so it's minus 15. So here we have 5. When we add all this up, we have 5 all to be squared. So it looked very complicated, but in fact what we have here is the minus there. 5 squared is 25, and then we divide by the 6 over here. So that gives us minus 25 over 6, which is minus 4.25, which is the value of our definite integral in that case. If we move on to the 6th question now, you'll see that finally we have a question here where we now have a power on the larger function. So, but the formula and the methodology is the same. So here we have 2 functions, the larger function, which is cubed, and the shorter function. So we start off by saying f at x is equal to the larger function. Now remember, we don't include the power, we just include the function inside the brackets. And on this side, we have g at x is equal to 2x. We follow our procedure, get the first derivative of f at x. So 3x squared is 6x, and that is our first derivative. To get a, we divide the coefficient of x in g at x by the coefficient of x in, sorry, I meant to use a different color pen there, the coefficient of x in f at x. So it's equal to the 2 divided by the 6, which will give us 1/3. And then the question is a times the first derivative equal to g at x? So is the first derivative of the bigger function a multiple of the smaller function within the product? And our answer here is 1/3 times 6x. So is 1/3 times 6x equal to 2x? So that's saying a times the first derivative of f of x, is that equal to g at x? And you can see here that it is, because 3 goes into 6 twice, so 2x is equal to 2x. Yes. So that means we can now use our formula. And once again, I'll write out the formula. A times f prime x times f at x to the power of n. And now we have a power of n greater than 1 is equal to a times f at x times n plus 1 divided by n plus 1 plus a constant of integration. Now we have a definite integral up here. We're going from 1 to 0. So if I come back here, so I'm do our rule here. So fill this in. So the integral from 2 to 1, a is 1/3. F prime of x is 3x squared minus 4. The function itself is 3x squared minus 4, and our power is 3. So n is equal to 3 in this particular case here. N is equal to 3. So when we go to apply our rule, well, a is 1/3. F at x is 3x squared minus 4. But our power was 3, and we raise it by 1 to 4, and we divide by the raised power. And that goes from our upper limit, which is 2, to our lower limit. Oh, I put the wrong powers in here, my apologies. Our upper power is 1. If you wait, I'll just rectify it. So our upper power is 1, and our lower power here is 0. I was getting confused with the last question here. So our upper power is 1, and our lower power is 0. So if we continue on here, to evaluate these functions, we can bring our constant outside. So the constant is 3 over 4, so we have 1/12. Open up our bracket, and we're going to evaluate this. So it's 3x squared minus 4 all to the power of 4 minus 3x squared minus 4. So you can see here what I'm doing here is I put the upper limit in here. So it's 3x squared minus 4, and here I put the lower limit in here, and that is also to the power of 4. So I've taken the 3 times 4 is 12. I've taken the 1/12 outside over here, and then I don't need such a big bracket there. I can use that one. And then it's a case of just evaluating these. So that is equal to 1/12. I don't like the way I've written that. It's not neat. So if I do it again, 1/12. So 3 times 1 is 3, minus 4 is 3 minus 4 is minus 1 to the power of 4. Minus, and here we have 3 zeros, minus 4 to the power of 4. So then if I bring this down here, that is 1/12 times minus 1. Any negative number brought to a positive power, minus 1 squared is plus 1. If I multiply by minus 1 again, I get minus 1, and that's minus 1 cubed. And if I multiply by minus 1 again, I have minus 1 to the power of 4, which is equal to plus 1. So remember, if the power is even and the number is negative, it will become positive. So minus 1 to the power of 4 is plus 1. Now minus 4, the same rule applies, so we should get a positive number here. Now 4, I think that 16 times 16 is 256. That's 4 squared. 4 squared. You add these together, it's 4 to the power of 4. So it's minus 256, like so. So what this gives us is 1 minus this is minus 255 over 12. And if you divide 12 into that, 12 goes into 25 twice with a remainder of 1. 12 goes into 15 once with a remainder of 3. 3/12 is a quarter, so it's minus 21.25. So our answer for the definite integral of this function up here is equal to minus 21.25. So if we then go down and look at question 6, same thing again, we have two functions. So we let f of x equal to the function with the higher power, and we don't include the squared. This is squared here, but we don't include that yet. G at x is the other function, which is 4x squared. So if we follow that, our same rule again, get the first derivative, same procedure again. 4 times, and the derivative of that is 3x squared. The derivative of 6 is 0, it's constant, so we get 12x squared. So our multiplier is 4x here divided by our 12x here. The coefficient of x squared in g at x, which is 4, divided by the coefficient of x squared in f prime of x. So that gives us a multiplier of 1/3. And then the question is a times the first derivative of f at x equal to the second function in the product with the g at x. So let's multiply this out. So 1/3 is 1/3 times 12x squared equal to 4x squared. And of course it is, yes. 3 goes into 12 4 times. So that is true. So that means we can use our formula. And our formula, once again, is as follows. A times the first derivative of f at x times f at x to the power of n dx is equal to a times f at x. And we raise our power by 1, and we divide by the raised power. And for an indefinite integral, we have a constant of integration. So if I come and apply this rule here, that says our integral, and we're going from where to where here? 1 to 0 again. So our upper limit is 1, our lower limit is 0. And what we're saying here is a is 1/3 times f prime x is 12x squared. So that will give us 4 of x, that will give us our g at x. And then we have our function here, which is, here's my f at x, it's 4x cubed plus 6b squared dx. So I've written everything out here. This is a, this is the first derivative of f at x, and this is f at x to the power of n, where n is equal to 2. And then I just fill that in. So a is still 1/3. Our function is 4x cubed plus 6. But now we raise our power here. It was 2, so we raise it to 3. So this becomes n plus 1. This is f at x, and this is a. So you can see here, you're raising this power here by 1. And of course, I forgot, we have to divide by our raised power here. And here, we're bringing this from our upper limit here of 1 down to our lower limit here, which is 0. We're calculating between the upper and lower limits, is the correct way to say it. So if I once again take the constants out, so we have a 3 here and a 3 here. So if I take that out, that's 1/9. And then I have 4x cubed plus 6 all to be cubed, going from 1 to 0. So that's a 9th times 4 plus 6 cubed minus 4, leave a gap for the x cubed. And I put in the upper and lower limits, so that's 2 cubed in here. And here we have 1 cubed. So that gives me, if I bring it down here, that gives me a 9 times 2 cubed here is 8. So it's 4 times 8 is 32 plus 6 cubed minus, and here we have 4 plus 6, which is 10 cubed. So that is equal to 1/9 times 38 cubed minus 10 cubed is 10 squared is 100 times 10 is 1,000. So I'll just calculate that short. Okay, apologies here. I put in the wrong limits again. So I'm making life hard for myself because that's a huge number. So what I should have put up here was 1 cubed in here, and here I should have put in 0. So if I recalculate now with the easier limits, because I made a mistake on those ones, that gives me 1/9 times, now here we have 4 plus 6 is 10, so it's 10 cubed minus, and here we have 4 times 0 is 0 plus 6, so we have 6 cubed here. So this is much easier. This gives me a 9th times 1,000 minus 6 cubed. So it's 1,000 minus 216, and that, if I bring it down here, gives me 784, subtracting that, divided by 9, 9 8s 72 with 6 over, 9 7 63 with 1 over, and I think it's 0.11 like so. So sorry for that, I put the wrong limits in there, but it's now the correct answer. So it's 87.11. Okay, thanks. Okay, we'll move on to the next one shortly. Or in fact, I'm going to finish that one here, and I'll start a new video for the remaining questions.